Welcome back to the deep dive. Today, we're jumping headfirst into maybe the biggest challenge in all of physics.
Definitely one of the biggest. We're talking about reconciling general relativity and quantum mechanics.
Yeah, GR and QM for, what, a century now have been, well, incompatible, right?
Pretty much. GR gives us this beautiful, smooth picture of gravity as space-time geometry on the grand scale. Think planets, stars, galaxies.
Right, bending space-time.
Exactly. But then you've got QM ruling the tiny world of particles and fields. It's all probabilities, discrete jumps, fundamentally different.
And trying to mesh them. Disaster.
You get infinities, paradoxes. The math just doesn't work when you try to describe gravity quantum mechanically using the standard approaches.
So our sources today introduce a framework aiming to, well, fix this, not just patch it up, but rebuild from the ground up. It's called the Quantum Unified Vacuum, or QUV.
And the specific model derived from it is Q-modified gravity, Qμ-Mg. It's the practical application, the part with testable equations.
And the central claim here is huge. It's saying gravity, even space-time itself, isn't fundamental.
Right. It's saying they emerge. They arise directly from quantum entanglement.
Okay, that turns everything on its head. Einstein's spooky action at a distance.
He hated that aspect of quantum mechanics, the idea that two entangled particles could be linked instantaneously, faster than light, no matter how far apart. It seemed to violate his own rules of relativity set within a fixed spacetime.
Because GR says nothing travels faster than light. That's the speed limit of the universe, built into the fabric of spacetime.
Precisely. And classical QM just says, well, they're correlated. Instantly. It doesn't really offer a mechanism that respects space-time, and critically, it doesn't explain any gravitational consequence of this link. Existing models just can't handle it. They fail to unify gravity with this fundamental quantum phenomenon.
So QUV comes along and says, well, what, that the spookiness is the point.
Sort of, yeah. It says entanglement isn't happening in space-time breaking the rules. It suggests entanglement is the very process that builds space-time. The spooky connection isn't a bug. It's the feature generating the geometry.
Wow. Okay, can you quickly clarify why we have these two names, QUV and QEMG, just so we're clear?
Sure. Think of QUV as the deep philosophy, the foundational idea. It's the framework saying geometry and matter emerge from quantum information, from entanglement.
The big picture concept.
Exactly. Then Qμ-Mg is the concrete gravitational theory that comes out of applying those QUV principles. It modifies Einstein's equations in a specific way based on entanglement, making it something we can actually test against observations and experiments. It's designed to give us GR back when entanglement effects are weak. Like locally.
Got it. So our mission today is to really dive into how QUV uses quantum information, uses entanglement, to basically dissolve that old boundary between gravity, source energy, and momentum, and the geometry it supposedly warps. They become two sides of the same coin. All right, let's unpack that core idea. Gravity, geometry, matter, all emergent. This means throwing out the classical picture, right? The idea of a fixed stage, a static space-time background for physics.
Completely. It's a radical shift. QEV proposes that space-time bubbles up from something more fundamental, a pre-geometric network. Imagine a huge interconnected web of quantum states, all entangled.
Pre-geometric. So before space as we think of it even exists.
That's the idea. Geometry isn't fundamental. It arises from the relationships, the information shared between these entangled quantum bits or nodes in the network.
Like pixels on a screen. Zoom in enough and the smooth image dissolves into discrete dots.
That's a great analogy. The smooth space-time we perceive, the one GR describes, is like the large-scale view of that incredibly dense quantum pixel grid. The geometry is an emergent property of the underlying quantum information structure.
And the sources mentioned a mathematical link here, this Olivier-Ricci curvature from discrete graphs.
Yeah.
How does that connect to Einstein's smooth curvature? That sounds really technical.
It is a bit technical, but the concept is pretty neat. Imagine you have a complex network, like, say, all the connections on the internet. Olivier-Ricci curvature is basically a way to measure how efficiently information can flow between any 2 points on that network. It's about the cost of communication.
Okay, like network traffic efficiency.
Sort of, yeah. Now, in smooth, continuous spacetime, the standard Ricci curvature from general relativity describes how spacetime bends, which also affects how things, including information, travel. What the QUV proponents found is that if you take their discrete quantum network model and make it incredibly dense, essentially zooming out from the pixels, this Olivier-Ricci measure of information flow mathematically transforms into the standard, smooth Ricci curvature of GR.
Whoa! So the math bridges the gap. The discrete quantum description naturally becomes the classical geometric one at larger scales.
Exactly. It shows a path from the quantum microstructure to the classical macro view. It's not just assumed, there's a mathematical convergence.
That sounds powerful, and it connects to other ideas in quantum gravity, doesn't it? Like causal set theory.
It definitely resonates. Causal set theory has this mantra: order plus number equals geometry. QUV is basically saying yes, and that order and number, the fundamental structure, comes from quantum information and how it's linked by entanglement.
Okay, if geometry is tied to quantum stuff, that must have huge implications for vacuum energy, right? The cosmological constant problem.
Absolutely. You can't have emergent geometry tied to quantum fluctuations and still hold on to the old idea of a fixed static vacuum energy. That's the source of that infamous crisis.
The one where standard QM predicts a vacuum energy density. That's, what is it, 120 orders of magnitude larger than what we actually observe.
Yeah, it's absurdly large. If it were that big, the universe would have, either instantly collapsed or expanded into nothingness. Something is fundamentally wrong with the classical QM calculation or its interpretation in a gravitational context.
So how does QUV handle this? Does it just wish the energy away?
Not at all. It reinterprets it using thermodynamics. It introduces what the sources call the first law of vacuum thermodynamics.
Okay, sounds important. What does it say?
It says vacuum energy isn't a fixed constant, it's a dynamic quantity. And crucially, it's screened, filtered, or dampened by the entropy of the universe.
Screened by entropy. So the universe's overall, let's say, informational messiness somehow regulates the vacuum energy's gravitational pull.
That's a really good way to think about it. The mechanism proposed involves the quantum entropy associated with all those virtual particles constantly popping in and out of existence in the vacuum.
The quantum foam.
Right. These fluctuations aren't just energy, they carry information, contributing to the vacuum's entropy. QUV argues this entropy acts like a dynamic filter, adjusting the effective gravitational influence of the vacuum energy based on the universe's overall state. So the raw energy might be huge, but its gravitational effect is tamed.
So it's not that the energy isn't there, it's that its gravitational effect is being actively managed by the universe's thermodynamics.
Precisely. It provides a physical mechanism rooted in quantum information and entropy, rather than just saying the constant is small for some unknown reason or introducing canceling fields.
The sources mention a constant in this context. What role does it play?
Zeta quantifies the screening effect. You can think of it as measuring the vacuum's total response to changes in geometry, integrated over all the relevant quantum fluctuations, all those virtual particle modes.
So it's like the efficiency rating of this universal entropy filter.
Exactly. It determines how effectively the universe's entropy screens the raw vacuum energy. It connects the microscopic quantum fluctuations to the large-scale cosmological energy density we observe. This makes the cosmological constant not just a number to be plugged in, but a consequence of the universe's dynamic entropic state.
That's really elegant. It ties the quantum, vacuum, thermodynamics, and cosmology together through information. Okay, now let's get to the absolute core of it, how QUV supposedly solves the spooky action problem. The claim is that the entanglement itself, described as the entanglement Hamiltonian, is the source of gravity.
This is the radical step. Classical physics failed because it put entanglement inside a pre-existing fixed space-time with rigid rules like the speed of light limit. That's where the conflict arises.
Because instantaneous correlation seems to violate that limit.
Right. QUV sidesteps that completely. It says the correlation isn't happening through space faster than light. The correlation, the entanglement, is generating the space, defining its properties locally. The interaction is the structure.
Okay. So how does that work mechanically? The sources put a lot of weight on the Unruh effect. I always thought of that as a kind of theoretical curiosity.
It's usually treated that way, yeah. But QUV elevates it to a fundamental principle. The Unruh effect is this bizarre but well-established theoretical prediction. If you accelerate really, really hard through what seems like empty vacuum.
You perceive it as being hot, like a thermal bath.
Exactly. You detect thermal radiation with a temperature proportional to your acceleration. QUV takes this connection between acceleration, temperature, and the quantum vacuum and makes it central to gravity.
And this is captured by the temperature operator?
Yes, Tsel is the key. It's defined as C$² equals C bar x to T bar. The crucial part here is axis, a proper acceleration at some point, or node cells in this underlying quantum network.
And where does that acceleration come from in empty space?
It's not acceleration through space in the usual sense. In the Qmon model, the effective acceleration x at a node is determined by the local space-time curvature. The formula given is x C2 Qμ-Inu.
Ah, I see. So the geometry itself induces an effective acceleration field, and that acceleration, via the Unruh effect, creates a local temperature.
Precisely. Curvature equals temperature locally. The more curved the spacetime region, the higher the effective Unruh temperature associated with that region's quantum vacuum state. It's the dictionary translating geometry into thermal information.
So the Unruh effect isn't just some weird thing happening to accelerating observers. It's the mechanism the vacuum uses to encode gravitational information.
That's the QUV proposal. It's the mediator. And now comes the critical link to entanglement. It's done via this coupling term in the theory. Sigma-X. Sigma-X.
Okay, let's break that down. T of X is the local curvature-induced temperature we just discussed. What's the sigma part?
That term, sigma, represents the strength or correlation of the entanglement between two neighboring quantum nodes, $x and $mlers, in the fundamental network. Think of it like how strongly two qubits are linked.
So the formula is temperature times entanglement strength. What does that multiplication do?
It means the local conditions the curvature encoded in TAGE directly influence how strongly quantum nodes nearby are entangled. If spacetime is highly curved in some region, high toxis sigma between the quantum degrees of freedom in that region are modulated. They get stronger or weaker in a specific, calculable way.
So curvature tells entanglement how strongly to bind.
Yes, and presumably the collective state of entanglement then feeds back to determine the curvature. It's a dynamic interplay. This isn't just pulled out of thin air either. The sources link this to the Bisoniano-Wichmann theorem.
Right, that came up. What's the significance of that theorem here?
Bisoniano-Wichmann is a really deep result from quantum field theory. It rigorously proves a connection between the thermal properties perceived by an accelerating observer, like the Unruh effect, and the entanglement structure of the quantum vacuum in that region. It shows they are mathematically intertwined.
So QUV is essentially taking that known mathematical link and saying, this isn't just math, this is the physical mechanism of gravity.
Pretty much.
Yeah.
The sigma-X sigma term is like the discrete physical implementation of the principle behind Bisoniano-Wichmann. It says geometry, via Dias governs, the quantum entanglement, sigma-X sigma, and vice versa.
Okay, that clicks. So entanglement isn't this weird instantaneous thing violating space-time rules. It's the underlying process that dictates the local space-time rules, specifically the curvature, mediated by these local Unruh temperatures.
Exactly. The spooky action is promoted from a paradox to the fundamental mechanism of interaction. Gravity emerges as a thermodynamic consequence of the vacuum's entanglement structure responding to curvature.
Which perfectly addresses why classical models failed. They have the relationship backward, trying to fit entanglement into a fixed space, rather than seeing space emerge from entanglement. Okay, this is a beautiful picture, but does it actually work? Does it solve any real problems? Qmn is specifically aimed at cosmology's biggest headaches, the Hubble tension and the dark matter puzzle.
Yes, and it tackles both using a single core concept, a scale-dependent gravitational coupling, denoted alpha.
Scale-dependent, meaning gravity's effective strength or how entanglement shapes geometry changes depending on the distance scale you're looking at.
Precisely. Alpha modifies the standard Einstein equations. It's designed so that for small distances, or high dollars like within our solar system, or even a galaxy cluster, the function alpha becomes very small.
So the entanglement modifications fade out, and we just get back standard general relativity, which works brilliantly on those scales.
Exactly. It recovers GR locally. But, and this is the key, as you look at much larger cosmological distances corresponding to small Tauler, the alpha K function grows. The entanglement effects become more significant, altering gravity's behavior on cosmic scales.
And that's how it addresses the Hubble tension.
That's the proposed resolution. The Hubble tension, just to remind everyone, is this nagging disagreement between measurements of the universe's current expansion rate, $, measurements based on the early universe, like the cosmic microwave background, CMB, give a lower value.
While measurements using local objects, like supernovae in nearby galaxies, give a higher value. And the error bars don't overlap. It's a real crisis.
Qmn's interpretation is elegant. It's not necessarily an error, it's physics. The CMB measurements are probing the universe on vast cosmological scales where Tellers is small and alpha K is active, modifying the expansion history predicted by the standard lambda CDM model.
Whereas the local measurements are probing smaller scales, where Tellers is larger, alpha K is suppressed, and the expansion looks closer to what standard GR predicts locally.
Exactly. The tension arises because we're comparing measurements made in regimes where, according to Qₚ, gravity itself behaves slightly differently due to these scale-dependent entanglement effects. The fundamental constant isn't truly constant across all scales.
So it provides a smooth transition. Emergent, modified gravity at cosmic scales, blending seamlessly into standard GR at galactic scales. That feels less like an ad hoc fix and more like a prediction.
Well, the specific functional form of alpha failure, it also depends on redshift error, or time isn't just tweaked to fit h$. It's supposed to be derived from the underlying entanglement principles and the ASQG framework we'll touch on later. That gives it predictive power.
Okay, that covers the expansion rate. What about the other big mystery? Dark matter. Galaxies rotating faster than they should based on their visible matter.
Qₚ makes another bold claim here. It can explain those galactic rotation curves without needing hypothetical dark matter particles.
Oh, if there's no extra mass, what provides the extra gravity?
It comes from another term in the modified equations, the beta term. This term generates what the sources call an entropic acceleration effect.
Entropic acceleration. That sounds a bit like MOND, modified Newtonian dynamics. MOND is often criticized for just changing the law without a deep physical reason. Is QUV just rebranding MOND?
That's a fair question. The proponents would argue no. While MOND modifies dynamics phenomenologically, basically, tweaking the formula to fit observations, QUV claims this entropic acceleration arises naturally from the theory's foundation.
How so?
If gravity emerges from the entanglement structure of the vacuum's quantum information network, then deviations from smooth GR gravity at large distances, where MOND-like effects appear, are seen as natural consequences of that underlying network structure. The acceleration is linked to gradients in the vacuum's entropy density, arising from the core principles, not just put in by hand.
Okay, so it's claimed to be more fundamental. What's the key test for any theory trying to replace dark matter on galactic scales? Usually it's the Tully-Fisher relation.
The baryonic Tully-Fisher relation, yes. The BTFR is this remarkably tight empirical law connecting a galaxy's total visible mass, stars and gas, to its overall rotation speed. Any alternative theory has to reproduce this.
And this Qmn?
According to the sources, it does. The model predicts the universality of the BTFR. It does this by linking the parameter beta governing that entropic force directly to another scale in the theory, the cosmic saturation scale, COSSIS. The relationship is beta propto 1 Qmn.
So the same underlying entanglement physics that modifies cosmic expansion also dictates how galaxies should rotate, baking in the Tully-Fisher relation automatically.
That's the claim. It connects the large-scale modification of gravity to galactic dynamics through these derived parameters, suggesting a unified origin for both phenomena rooted in entanglement.
Impressive if true. Finally, consistency check. Black holes. Any unified theory needs to get black hole thermodynamics right, particularly entropy.
Absolutely. It has to align with the Bacon-Stein-Hawking entropy formula and ideally predict the expected quantum corrections.
On Qmn.
It seems consistent. It correctly predicts the leading logarithmic correction term to the Bacon-Stein-Hawking entropy, something proportional to a kilolog, where A is the area and LP is the Planck length.
That specific logarithmic form isn't unique to Qml, though, is it?
No, and that's actually a strength. That same form of correction pops up in other respected approaches to quantum gravity, like string theory and loop quantum gravity via 8SCFT. Finding it here, too, suggests Qmn is on the right track mathematically, consistent with general expectations for quantum gravity effects.
But the sources say Qmn goes a step further. It calculates the coefficient of that log term.
Yes, it calculates the prefactor, which we called alpha earlier in a different context, but here it's the coefficient of the log term in the entropy formula. The theory gives a precise value, alpha Qₘₙ Qₘₙ. Note the appearance of zeta, Apéry's constant, connecting to that vacuum response factor, zeta del zeta.
And plugging in the fundamental constants, that number is?
It's absolutely enormous, something like 172 times 10 units of K2. Just a staggeringly huge number.
Why is that number so massive? And why is calculating it precisely such a big deal?
The sheer size highlights how incredibly sensitive black hole entropy is to the fundamental quantum structure of spacetime. Entropy counts the underlying microstates, the ways the system can be arranged. Getting such a huge, precisely defined coefficient suggests the theory has a very specific, very dense microscopic structure for spacetime built from these quantum information principles.
So it's not just getting the form right, it's quantifying the underlying quantumness in a very specific, non-arbitrary way.
Exactly. It moves beyond just conceptual consistency and makes a hard, quantitative prediction about the fine-grained nature of quantum spacetime derived directly from the entanglement framework. It suggests the theory has the microscopic details needed to explain black hole thermodynamics from first principles.
Okay, so QUV presents a compelling story, tying together entanglement, geometry, cosmology, and black holes. But ideas are one thing, proof is another. For this to be physics, it needs rigorous testing. The coupling constants alpha, zeta, they can't just be knobs tweaked to fit data.
Absolutely not. They need a deeper theoretical justification. That's where the connection to asymptotic safety, ASQG, becomes crucial for the QUV program.
Asymptotic safety. That's the idea that quantum gravity might regulate itself at high energies.
Sort of. ASQG proposes that quantum gravity could be fundamentally consistent and predictive all the way up to infinite energy, the ultraviolet, or UV, because its fundamental constants don't blow up. Instead, they flow towards a stable, interactive fixed point in the theoretical landscape described by the renormalization group, RG.
Can you unpack that RG flow idea a bit?
Imagine the fundamental constants of nature, like the strength of gravity or electromagnetism, aren't fixed numbers, but change depending on the energy scale you're probing. The RG flow describes how they change. Think of it like skiing down a mountain representing energy scales. ASQG suggests that at the very top, highest energy, there's a specific stable point, the UV fixed point, where the theory is well behaved. The values of constants we measure at low energies are determined by how they flow down from that point.
So embedding QUV in ASQG would mean its parameters, like alpha and beta dollar, aren't arbitrary inputs. They'd be outputs of this fundamental RG flow, determined by the UV fixed point.
That's the goal. It would provide a fundamental UV-complete origin for these parameters, ensuring the theory is mathematically sound and predictive from first principles, not just a low-energy effective model. It gives it that theoretical backbone.
Okay, so that's the theoretical underpinning. What about actually testing it? The sources talk about a three-pronged approach.
Yes, a multi-messenger strategy. If QUV is right, the same underlying physics, the same function, must consistently explain observations across three totally different domains. Laboratory experiments, astrophysical surveys, and cosmological data, they all have to line up.
Let's take those one by one. Pillar 1, the lab. This seems to focus on directly detecting the Unruh effect, the theory's cornerstone.
Right. Detecting Unruh is incredibly hard because you need insane accelerations to get a measurable temperature. But experiments are getting more sensitive. The sources highlight LUXE, the Light on Extreme Fields experiment.
It's new there.
Advanced simulations for LUXE's upcoming phase predict they could significantly boost the signal. Specifically, they expect the ratio of Unruh-generated photons to background Compton-scattered photons to increase by maybe 2 orders of magnitude compared to earlier attempts like Facet 2.
2 orders of magnitude. That's a factor of 100. Does that make it actually detectable?
It might just push it into the realm of possibility. If they can measure a thermal photon bath consistent with the Unruh prediction for the accelerations involved, and importantly, if that temperature Tₘₙ matches the Qmot prediction based on whatever serves as the local curvature proxy in the experiment, that would be huge. It would be direct evidence for the core mechanism linking geometry, acceleration, and thermodynamics.
Okay, that's the fundamental check. Pillar 2, astrophysics. Looking for evidence in the structure of the universe itself.
Exactly. This involves looking at large-scale structure, the cosmic web of galaxies and clusters mapped out by surveys like SDSS and BOS.
What are they looking for?
They're trying to see if the geometry of that structure correlates with measures of entanglement. Preliminary analyses mentioned in the sources use that Olivier-Ricci curvature as a proxy for the geometry of the galaxy network, and they compare it to some calculated proxy for entanglement entropy within that structure.
And they found something.
Tantalizing hints. The sources report a statistically significant correlation, with a p-value below 0.01, suggesting that regions with certain geometric properties, as measured by curvature, tend to have different entanglement characteristics.
So the shape of the universe on large scales might actually reflect its underlying quantum entanglement patterns.
That's the implication. But, strong caveat here. The sources stress this is exploratory. It's not definitive proof yet. It's more like smoke, suggesting there might be a fire worth investigating more closely. It points towards a potential observable effect of the entanglement geometry link predicted by QUV.
Got it. A promising lead needs more work. Pillar 3, cosmology and gravitational waves, using the whole universe as a laboratory.
Right. Gravitational waves detected by LIGO Vergakagra are incredibly useful here. Qμ, with its scale-dependent coupling alpha, predicts that gravitational waves might not travel exactly as they do in GR.
How would they differ?
The theory predicts a modified dispersion relation. Omega 2 equals C2 K21 plus alpha K ln Z. This means the speed or propagation of a gravitational wave could depend slightly on its frequency, related to KdE. By precisely timing signals from merging black holes and neutron stars across different frequencies, we can put extremely tight constraints on any deviation from the standard GR prediction.
So gravitational wave data probes the high-frequency, small-scale behavior of alpha K complementing the large-scale cosmological tests like the Hubble constant.
Exactly. It tests the theory in a different regime. Now, there's a crucial update here regarding another cosmological probe, the CMB lensing anomaly, Allen's all.
Ah, yes. This seemed like a big piece of evidence for modified gravity theories. What's the news?
Well, for years, CMB data seemed to show a slight preference for more gravitational lensing than predicted by the standard lambda CDM model, quantified by this parameter Allen's O as being slightly greater than 1, maybe around 1.02 or 1.03. This was often interpreted as potential evidence for theories like Qμ that modify gravity or expansion history. But the latest analysis from the Planck collaboration, the PR4 data release, shows that this anomaly has significantly weakened or even vanished altogether. The preference for Allen's IO is largely gone in the new data.
Wow. Okay. That's a major shift. What does that mean for testing QUV?
It means one of the key pieces of circumstantial evidence that seemed to favor models like Qμ has evaporated. It forces a strategy shift. While cosmological tests like H$Delta and constraints from gravitational waves are still vital for checking the consistency of alpha psi across scales.
The pressure is now really on the laboratory tests.
Exactly. The sources suggest the burden of initial validation now falls much more heavily on experiments like LUXE. Detecting the Unruh effect, confirming that core mechanism directly, has become the primary hurdle. If that fails, the motivation dims significantly. If it succeeds, then the cosmological and astrophysical tests become crucial for confirming that the specific scale dependence predicted by alpha Z matches reality across all domains. The Allen's result makes the lab test absolutely critical. ###atro.
So after this deep dive, Qμ really offers a profound rethinking of our universe. It takes entanglement, Einstein's spooky action, and says, no, this isn't spooky, it's fundamental. It's the engine building spacetime itself.
Yeah.
It aims to heal that century-old rift between GR and QM.
It's a beautiful conceptual leap. The proposed mechanism curvature setting local Unruh temperatures, which modulate entanglement, which in turn sculpts geometry, provides that missing link. But beauty isn't enough in physics.
Right. The whole thing hinges on whether that single, specific, theoretically derived function, alpha zeta, the scale-dependent coupling, can simultaneously explain results from lab benches, galaxy surveys, and cosmic observations.
It's an incredibly demanding test. Those three, Windows Lab, astrophysics, cosmology, probe such vastly different scales and phenomena. Getting one function derived from entanglement principles to satisfy all three would be revolutionary.
And thinking about that scale dependence, if QUV is right, and even something as fundamental as the Hubble constant isn't truly constant, but depends on the scale you measure it at because alpha K is mediating it, that makes me wonder about the future.
How so?
Well, we search for fundamental constants, right? Things we assume are the bedrock of reality, unchanging. But if this theory is correct, maybe many constants are only constant within the energy range or scale we've been able to probe so far. What happens when we build future experiments that probe vastly different scales? Could we find that even things like the fine structure constant, or Newton's G, are also scale-dependent, flowing according to some deeper RG logic tied to quantum information?
That's a profound implication. If unification inherently involves scale dependence mediated by something like entanglement entropy, then our whole notion of fixed, immutable, fundamental constants might just be an approximation, an emergent property valid only in certain regimes. The true constants might be the parameters of that UV fixed point in ASQG, with everything else flowing dynamically from there. The constants we measure could be running constants in a very real sense.
A universe where even the constants aren't constant. That's definitely something to chew on.
Indeed. The search for unification might reveal a reality far more dynamic than we imagine.
And on that thought, thank you for joining us for the deep dive. We'll see you next time.